I'm Edward Hu, and I'll be presenting Planning Goals for Exploration. This is joint work with Richard Chang, Oleg Rybkin, and Dinesh Jayaraman at the University of Pennsylvania. So let's start with the setting, which is unsupervised task discovery. So in unsupervised task discovery, we drop an agent into an unknown environment. So for example, we might start a household robot up in a kitchen for the very first time. In the exploration phase, we figure out what can be done in the environment and how to do it. Then in the evaluation phase, we set arbitrary new tasks in the environment. So maybe we let the robot run for a day and it's going to play with the kitchen utensils or open some drawers and in general figure out the affordances of the environment in the exploration phase. And then the next day, I can just ask the robot to clean up the kitchen counter without having told it that in the exploration phase explicitly. So it's quite clear that the more diverse experience gathered in the exploration phase, this enables the agent to learn a wider variety of tasks off that diverse data, and in turn, you get a more generalist agent. So let's talk about task discovery in goal condition RL. So in goal condition RL, you train a goal condition policy pi of g to reach any specified goal state g. And here we're using states as g, so it's about reaching a particular state as a task. So hopefully by the time you train your policy at evaluation time, you can just set arbitrary new tasks. Like in this 2D MDP, you can see that if we set just arbitrary new points like this green star or this orange star, the goal condition policy will go towards that. But how do you actually get this? So the key to getting this is actually during training time, you need really good exploration of the environment to get that data needed. So what people do is often they use something called go explore exploration, which basically switches between a goal condition policy pi of g and an exploration policy pi of e in a single episode. And this basically reduces the horizon of your exploration and gives you much greater exploration ability than normally just like running out a single exploration policy. So one thing that I haven't mentioned is actually how to choose goals for Go Explore. And the paper itself doesn't prescribe a very general way. So intuitively, we should set diverse goals to generate diverse data. But what does that mean? Like the definition of a diverse goal is actually rather nebulous. So as you can imagine, a diverse goal might be an unseen goal, so it might not be seen in your data distribution. Or maybe if you have like joint limits, it might be like a goal state with the joint limits are set to negative infinity. Like that doesn't make sense, but it could still count as a diverse goal. But you also don't know if the goal condition policy can actually reach it. So just, the definition of a diverse goal is nebulous. So we're trying to answer this general question of how should an agent choose goals to maximize exploration. So our key insight is to optimize for the exploration rewards accrued by the exploration policy pi of e during the exploration phase. So to build some intuition, here's like that training episode where you're trying to roll out a goal condition policy. And when you pick goals, basically what you want to focus on is you want to pick these goal stars such that the terminal states of the goal condition policy end up in a place that's good for exploration. And note that this is very different from just directly setting the goal state as like a frontier state. You're actually reasoning about this terminal state distribution of the goal condition policy because it is suboptimal. So if we write this in an equation, we can see that there are two parts. So we're first maximizing for a goal variable g, and we're reasoning about the terminal state distribution of the goal condition policy conditioned on g. And we're measuring how good this g produces a terminal state such that when you roll out an exploration policy, you'll get high exploration value. So to actually do this in a sample efficient manner, you don't want to just do this in the real world. That'll take forever. Instead, you want to have some model or some way to foresee where the goal condition policy will end up when you give it an arbitrary goal variable g. So what we can do is we can just learn a world model and do everything in imagination. So this is a really quick run through of our method. What we do is we just arbitrarily sample goal candidates. So this can be from your replay buffer, or if you have knowledge of like the joint limits, for example, you can just sample from the joint limits, any distribution. And then what you do is you use the world model, and you're going to predict how the goal condition policy will roll out when you condition it on these goal candidates. So maybe for the orange star, it'll look something like this. And for the purple star goal, your terminal state will end up looking like this. Then it's very simple. So to score these goals, what you do is you just look at the terminal states, and you can see in this purple goal example, the terminal state is rather near the frontier. So actually the exploration value function, if you're training it correctly, it will predict a higher exploration value. So here, we're saying it's good. And you can see likewise for this orange star goal, it's actually more poor. And what's very interesting in this example is that the orange star goal, if you just took the value function of the orange star goal directly, it would have high exploration value. But since we're actually reasoning about how the goal condition policy rolls out with respect to the goal condition policy, we can actually more intelligently select goals that give us high exploration value. So we will just use the purple star for Go Explore. So here's the overall training loop. So what we do is we generate a goal using the algorithm I just described, and then we perform a round of Go Explore exploration where we use that goal for the Go phase, and then we switch to the undirected exploration policy, which is usually maximizing some intrinsic motivation reward. And then we run a round of model-based RL off of this very informative trajectory. So we're improving the world model, the policies, and the value functions. And basically, this is a nice positive feedback loop. So with a more accurate world model, you can more accurately approximate that terminal state distribution. So we just repeat this until convergence. So going into the actual baselines, I'm not going to explain each one very deeply, but all of these are basically state-of-the-art exploration baselines, and they're actually all model-based RL. Baselines, and we basically compare against baselines that either use Go Explore or they try to be intelligent about the way they choose goals. So for example, you might have like a kernel density estimate of the goals, and SKUFit and Mega will just pick goals that have lower density, basically. But for example, they don't reason about the actual exploration value of the policy, making them not fully like aware of the Go Explore phase. Whereas for PEG, our method, we directly compute kind of the exploration value of the Go Explore strategy itself. So we have 4 environments. We have navigation, walker, ant maze, and block stacking. So just really quickly, so these are like the curves, where the curves are basically, as we're training these agents with that unsupervised exploration objective, we're periodically evaluating them on unseen test goals. So there's no leakage of like information about the test goals during the training time. We're just seeing basically how good these goal condition policies can achieve these held out test goals as it's exploring. So basically, the better you explore, the higher a curve should be. And our curve, the blue curve, outperforms all of them, especially in the block stacking case, which is the hardest environment. So I'll go a little bit more into detail. So you can just see these are some rollouts of the converged PEG policy in all of these environments. So in the point maze, it quickly reaches the top right corner, which is the furthest away from the bottom left spawning point. In Walker, the goal condition policy can do multiple reaching locations, etc. I'll be a little more in detail soon. So in the Walker example, the exploration is quite interesting. So when it does Go Explore, the goal condition policy first runs as far as it can to its own capability, and then the exploration policy takes over and does some flipping. So you can see in these examples, it's either running backwards or forwards and then doing some cartwheels. And then because of this, we're able to get very good evaluation time behavior where the walker is able to run somewhere and then stand completely to a standstill. Next, in the ant maze, we also see some similar behavior where the goal condition policies like navigating the ant smoothly around corners. And then once it gets to the desired goal point, it's going to switch to the undirected plan to explore policy. And once again, we can just condition evaluation time, we can condition it on these arbitrary goal states and expect a reasonable policy. So if you actually analyze what's happening, so we can look at the replay buffer and the chosen goal states for each method. What we see is that the green states for each method, which is basically the replay buffer, you can see that the PEG replay buffer is more expansive in this hallway than, for example, Mega and SKUFit. There's a lot more green states or seen states in the top left corner. And what's very interesting is if you look at the goals that are being optimized by PEG, you can see that the goals are actually they're actually in the walls of the environment. So PEG is actually able to take advantage of this fact that we don't care about what kind of goal we're optimizing. As long as we predict it to have high exploration value, we should use it. To finalize the experiment, I think our block stacking results are the most interesting. So what's basically happening is in Go Explore, the goal condition policy is actually stacking blocks into 3 stacked block towers, which is very interesting. What's happening is basically the 3 stacked block tower state is a very high exploration value state for the exploration policy. The reason why is from a 3 stacked block tower, you can basically mess up the tower in a very chaotic way. You can throw it out, or you can mess up all the blocks together. And that's going to give you a lot of intrinsic reward over doing something to the blocks individually. So that's why PEG is able to explore very quickly, and we're able to get 3 block stacking. And that's pretty much it. There's a code base. In general, PEG exploration allows us to train goal condition RL policies to become generalists in a novel environment. We propose goals that maximize exploration value inside a world model. And please come to my poster if you want to hear about the interesting limitations in future work. Thank you.
Hey, thanks for the talk. It's very interesting work. So I have a question about the block stacking task. So I noticed that in your task, you're just trying to stack 3 blocks into a tower, right? But maybe like we want to build some structure that's more complicated. And you were saying like, after stacking three blocks, you can just like leave out the lower one, and then that will create a very chaotic state. But how do you think the method can work to like explore some more complex block structures where you need to like where you need to stack blocks in a specific way?
I think that's a very good question. So unsupervised exploration in this regard only tries to find new states. So if your block tower, for example, if it's a good starting state to get perturbed in, then like we have hope that unsupervised exploration can find this state. But if you need a very particular configuration, then it might not even be high in unsupervised exploration reward. That's where you want to bring in like demonstrations or task rewards or some prior. Thank you.